Sonny left you a gift. Y'all been looking at it. Anybody want to speculate what this is? The rain in Spain, but not in Portugal. Portugal obviously did not participate in this mapping project. Neither did Italy. It doesn't look like Switzerland participated. Denmark did, but the other Scandinavian countries did not. So let me see. Greece did not participate. Anybody want to speculate what this is? Nobody's going to speculate because you're always wrong in Sonny's class, right? Okay, here you go.
Is it Walmart?
Oops. Earthworms.
I think we can be excused for missing out.
I had no idea why my wife forwarded this to me. And then she said it's a gift from Sonny to the class. I met my wife at Defense Mapping Agency. At that time, she was director of that portion of the Defense Mapping School that handled geographical information systems, GPS navigation, which, by the way, was brand new at the time. And at that time, they were calling it multispectral imagery, which is tough to say. They changed it to remote sensing to make it easier for us folks. She had a top secret compartmented security clearance, and she briefed ambassadors and high-ranking officers from foreign countries who were about to receive intelligence from our intelligence community based on remote sensing. And I'm telling you, when I first met her, not that she isn't now, she was hot. And she used to be a regular fashion show at these presentations to these people. And she was the first one up. Now they're going to receive intelligence that we got from satellites and other places. She's going to brief on that, but she helps them to understand what they're going to get. Some of them had no clue what was about to be placed in front of them. And so she began to talk to these people, walking around, this hot blonde babe, giving a lecture. And you want to know what the truth of that was? None of us wanted to follow her. We were the ones that would actually present the intelligence. First thing off the bat is GPS. Oh, by the way, at the Defense Mapping School, where Sue was the director of this department, for each one of these courses, you got college credit. And Sue was responsible for the ACES, and I forget what the other agency was. She was responsible for maintaining the accreditation. So in many cases, when I go through these two classes this morning, I'm going to be directly quoting her. And if I remember that I'm directly quoting her on something, especially multispectral imagery, I'll remind you. The first class today is Global Positioning Systems. Now, if you go to sleep in the class, I won't do anything about it unless you snore. Much of this information comes from the Air Force, and there's a real handy site called www.gps.gov. And I have to tell you that much has changed since I left that environment in 1991. 1991 was the last time I had anything to do with this in its military format. Much has changed. A lot has changed. I've grown up a little bit since learning this lecture. GPS is a constellation of satellites. These satellites orbit around the Earth for some useful purpose. That useful purpose is to aid in navigation. At the time that I started doing this, there were 24 satellites. There were actually 27, and 3 of them were spares. One of the spares didn't work, but we didn't want anybody to know that. One of the spares was powered by a thorium clock, and the rest of them were powered by cesium clocks. Not to worry, I'll tell you what happened to the one with the thorium clock. There are 24 satellites plus 3 spares. They are in 6 orbits around the Earth. Actually, that's wrong. There are 31 of them now. Some of them coming into service, some going out of service. They are at a 55-degree inclination from the equator. You have to have that particular orientation in order that you can see 4 satellites at any one time from anywhere. They are at an altitude of 20,180 kilometers above the Earth, and their orbits are so close to being perfectly circular that the ratio is 0.02% warpage of the orbit as it goes around. It is nearly perfectly circular. There are 6 planes with 4 satellites in each plane. There's 4 satellites in each orbit going around the Earth, plus some spares that are not actually turned on and visible at any one time, because they have to maintain, I'll get to that in a second. They are moving at 3.9 kilometers per second, so that's pretty fast. So that means that they go around the Earth in 11 hours, 52 minutes, and 2 seconds. That's how long it takes them to go around the Earth. So they do this twice a day. Meanwhile, underneath them, the Earth is rotating. So you don't get the same 4 satellites. 1 hour from now, you will not get the same 4 satellites. And I'm going to show you how you know what you're looking at. So there's 2 cycles per day. And they must maintain, in order for you or your GPS receiver or your car or your airplane or what's her name you talk to on your phone? Siri? In order for Siri to know where you are, Siri has to have 4 satellites. Otherwise, you're toast. You don't know where you are. And I'll explain to you how that works. The first satellites that came along were in Block 2, the Block 2A satellites. There aren't anymore. They went away, especially the one with the thorium clock. He went away he was the first one to go. So there are no more of those satellites operational. Those were the ones that came about in the beginning. They were the ones that were first turned on for you to see. Now, there were satellites that you couldn't see before 1990, but those are the ones that started the program. Then came the Block 2Rs. These only were planned to last for 7.5 years. There are 11 of them, and they are still working now, and we're a lot more than 7.5 years later. They are still working, some of them. Then came the next Block 2, RM. This has to do with correcting, making corrections. The satellite helping you to correct your GPS receiver on the ground so you know a little more accurately where you are. And how many Navy people do we have here? Any ex-Navy folks? Come on. You Navy veterans? Good. We can poke at them. We're going to poke some fun at them later on. There are 12 operational of the Block 2F, and there's one of the brand new Block 2 and 3F. Now, what do these things do? Well, it's all about accuracy. You've got to know where you are, and I'm going to talk about accuracy, how it relates over the years. You really need to know where you are, because when the first ones came out, I could tell where I was usually somewhere between 90 and 100 feet. Now, if you lose your car and you can't find it and you're 90 feet from it, then you must be at Walmart. The Soviets also decided they were going to launch their own satellites, and they did. It's called GLONASS. And I'll let you read this for yourself. Here are the two satellite systems compared to each other. They have 24 of them, at least 24. We know how many they really have, but for public consumption, they have 24. Why do they have 24? Because they have also 6 orbits with 4 satellites in each orbit. They're at a lower altitude than we are. So the closer you get to the Earth, then the satellite speed changes. But they're not going to run into ours, because not only are they closer to the Earth, but their orbital plane is inclined differently. So their orbits are not the same. Say what? Yeah, I'm sorry. That 19,130 is not correct on ours. I don't know where this slide came from, but that is not correct. It's 20,180 is ours.
It's only 30 feet different? Oh, kilometer. Yes.
So how does all this work? Well, here you are standing on the face of the Earth, and you've got a GPS receiver of some kind. And remember, I told you, how many satellites do you have to see? So if you don't see 4, you're not going to get your location. In the early days, guess what? There would be times when you couldn't see 4 of them. And the reason you couldn't see 4 of them is because your receiver ignores anything that's below 15 degrees above the horizon. So even the satellite might be rising to where you're just about ready to see it, you couldn't. So if you can't see 4 satellites, you're going to kind of be lost.
You're not meaning really seeing them, are you?
Your receiver, yeah, your receiver being able to detect them.
I don't remember.
Now, no, you can't see them. They're very small. Not yet. Not yet. So here's your 4 satellites. I've got them color-coded. They probably all look like aluminum foil if you really looked at one. So you know how far you are because they calculate the ephemeris. In other words, they calculate the orbit of this satellite. So the satellite knows where it is, and your receiver knows where it should be at that time of day. It gets that information from the satellite. The first thing the satellite downloads is the ephemeris. Also, the satellite tells you when the signal left the satellite. And your clock and your receiver knows when you got it. So how many seconds do you think it takes to go 20,000 kilometers? A very tiny, itsy bitsy part of a second is how long it takes for that signal to get to you. So these computers have to be pretty smart in order to hold one in your hand, and it's going to talk to the satellites. It's actually going to talk to at least 4. And it's going to get the time that it takes for the signal to get from each one of those 4 satellites. So if that happens, then you know the distance from you to the satellite. You know when the signal left. You know when you received it. You know what the speed of the radio signal is, which is 181,000 miles per second, in case you want to know. So you know at what speed that the signal travels, so therefore you know how far you are from that satellite. And then you know how far you are from this satellite, the mauve-colored satellite. And then you know how far you are from the green satellite. There's a little bit of ambiguity right here. See that? They don't exactly cross at the same spot, do they? So you are somewhere in that triangle. So then any 2 of those satellites will talk to the 4th one. And then it starts doing an iteration between groups of 3. This group of 3, that group of 3, this group of 3, whatever. It starts an iterative conversation and an iterative calculation until it gets this tiny little area down here very small. There's a lot of things that can happen to that satellite signal. There's a lot of things can happen to the little device in your hand that's powered by AA batteries. So how small can you make that triangle? We're going to tell you how that happens. There's all kinds of error, which means that you can't pinpoint your spot on Earth. That creates problems with your accuracy. There's things that cause those errors. The first one is the ionosphere, a highly charged environment that the satellite signal has to pass through. So on its way to you, that satellite signal is passing through a highly ionized layer in the, I guess it's not the atmosphere, a layer around the Earth, the ionosphere. And so that's going to cause about 4 meters of error. 4 meters. At somewhere between 13 and 15 feet. So right away, as soon as the signal leaves, passes through the ionosphere, you're wrong by 15 feet. It could be as much as. The clock. Now I'm talking about the clock on your GPS receiver. This thing. I'm not talking about the clock on the satellite, because every time that satellite passes over Falcon Air Force Base, which they renamed something else, and Diego Garcia in the Indian Ocean, they correct the clock on that satellite. And also, as the satellite is going around the Earth, when it passes over the Himalayas, it gets closer to the Earth. And as it passes over the Marianas Trench, it gets farther from the Earth, because of the gravity interaction with the orbit of the satellite. The orbit of the satellite is really not as smooth as you think. It's a lumpy, bumpy affair. The ephemeris, the ephemeris are changes in the orbit of the satellite. Well, the satellite doesn't know it's wrong till somebody at Falcon Air Force Base or in Diego Garcia uploads a correction to it and says, oh, you're wrong, and this is by how much you're wrong. And so it remembers that until it passes over those points again. Now, there are other stations around the Earth that are aware of the satellites and know what their error are, but there's only 2 control centers. Falcon Air Force Base, which is whatever they call it now, and Diego Garcia. The troposphere, believe it or not, just the presence of air affects the signal from the satellite. just having to pass through air causes some problems that degrade the satellite. And your GPS receiver is not the most fantastic computer on the face of the earth. Multipathing. If that satellite signal were able to get into this room, it would bounce off the walls and the ceiling and the floor. And what happens is your receiver doesn't get one signal, it gets a bunch of them. It gets the one that comes directly from the satellite and the ones that bunch around, that bump around all over the place. So unless you have a direct, clear view of the satellite electronically, you're not going to get a single message from the satellite. You get multiple messages. That's called multipathing. If you add all that up, you could be wrong by what? 35 or 40 feet. Believe it or not, they have worked it out. And we're going to show you how close you really can get. So here's how we're going to get rid of the errors. There's 4 basic systems. WAAS, Wide Area Augmentation System. That is a series of stations on Earth that are uploaded to another satellite that is not a GPS satellite that transmits the message to the satellites and giving them error corrections. The first GPS receivers that came out did not have that. Differential GPS. Differential GPS is where there is some station nearby, or some government established station, or a temporary station you put up over a benchmark that knows exactly where it is. And if your receiver can contact that device, then it will tell your receiver how much each satellite is wrong by. It'll send a time correction to your receiver that says, hey, you're wrong by this amount of time. You know how small that is when the satellite signal travels at 181,000 miles per second? It is a small correction, but they're able to handle it. You can say, okay, I give up today. I'll go home and figure it out when I get home. You can actually download correction data from these core stations that you can use to correct your data. I have done this twice and gave it up after that. Besides, I didn't process data when I got to my home. I had to process it in my hotel room after everybody else has gone out eating and drinking. I'm in my hotel room processing data, so I know exactly where these points were. And the last one is OmniStar. You see that L-band frequencies? All those new satellites are doing this for you. It used to be you had to contact OmniStar, which was a satellite, and say, okay, what are the corrections? But now, with the new satellites in orbit, these latest versions, you don't have to do that anymore. It figures it all out in the satellite when it sends a signal to you. The reason being is you can't transmit a signal very well from a handheld device. Now, I've had some devices made by Atlantic Instruments and by Trimble and so forth that I've used professionally that can contact other devices to do the differential GPS corrections. So this is how this works, differential GPS. Again, here we have 4 satellites. We have a rover, that's this guy here, or some device that's capable of getting a radio signal. You can dial up a radio station. Every single fixed station and every single portable station that you set up there over a known point on the face of the earth sends out its correction signal on a certain frequency. And all you got to do is dial in that frequency, like tuning your radio, and you get the corrections from that station. Well, you've got a rover and you get these satellite signals, but you know where you are. You have a measured location, but remember underneath the little girl how ambiguous that was? I'll tell you where it really gets bad is when those 4 satellites are close together. You know what those circles look like at the bottom when the satellites are close together? That's called geometric dilution of precision. Anyhow, you have this measured location, but you have a base station somewhere that knows exactly where it is. So it asks the satellites, where am I? Satellites tell it where it is, or it calculates from the signals from the satellites. And the station says, no, that's not right. That's not where I am. So that station starts fooling with the time signals from each satellite until it can resolve exactly where it is. And when it starts fooling with the time signals, it will send that correction to your receiver. And your receiver applies that correction. Base station gets its signal, corrects it in terms of time, and sends that time correction to your device. And that's how. This is a portable base station. You can rent these or have somebody set it up over a base mark for you. It is very expensive to get that done. Now, I bet that Auburn University has one of these. That thing, somewhere on Auburn University, knows exactly where it is. And it transmits over a very high-powered radio system, not powerful enough to go more than 150 miles, but anything within 150 miles you can dial into it. And when you can talk to this puppy, and there's usually one at every university, in every like radio station facility, very substantial radio stations and TV stations will have these. And you just have to know where the nearest one is. It's called a CORS station. You can look it up on the internet and find out where the nearest one to you is. C-O-R-S, CORS, not C-O-O-R-S like beer. But you can look up the nearest CORS station and it'll tell you how to tune your radio to that station. And this thing is sending out a signal to your device, and it makes your device a lot more accurate. This that you're looking at there is this device. And I'll lay it down here. Y'all can look at it during the break if you want. But I would turn it on, except for it cannot possibly receive the satellite signals in here, in this building. As a matter of fact, if I turn it on right now, it'll ask me, are you in a building? It does. It actually says that, are you in a building? But what you're seeing here is each one of those circles. Notice there are a lot more than 4 in this picture. Each one of those circles is a satellite. And down here at the bottom, like here's satellite number 3. Satellite number 3 has a very high signal strength. But satellite number 87, wherever he is, this one, he has a very low strength. Why is that? Because he's just emerging from that 15 degrees above the horizon. He is just coming up to where my GPS receiver can detect him. And the higher they get in the sky, the higher they get in the zenith, in the heavens, the stronger their signals. In this case, look at how many satellites there are, plus a Russian one. This thing here is actually able to talk to the Russians. It's WAAS enabled. So I have a corrected GPS in my hand. And you know how much I paid for this GPS? Less than I paid for my first one. And it's not corrected by anything. Well, actually, I think maybe I can turn WAAS enabling on this one. This tells me how accurate it is. So the GPS, plus being able to talk to GLONASS, plus being able to talk to WAAS, enables me to know where I am within 9 feet. Now come on, I own a white Toyota Camry. It looks like every other white car in the Walmart parking lot. If I can't find it within 9 feet, then I'm missing something there. I'll go around the back and see if my wife's Alabama sticker is still there. Accuracy versus precision. We're going to have a test here, okay? Is that accuracy or precision? That's accuracy. The bullets all landed in the center. You were aiming for the center, and the bullets mostly landed there. So that's what we would call accuracy. What is this? That's precision. All the bullets landed closer together. They didn't quite hit the target, but they all landed closer together. You can fix that. You can fix that with your GPS. You can move those bullets over so they look like this. So what do we now have? Accuracy and precision. Okay? The differentially corrected GPS, the WAAS-enabled GPS, and the GPS that's able to talk to GLONASS can move you to look like that. How close can it move you if you have a differential GPS system where you could talk to a core station? That close. Surveyors have less than centimeter accuracy using GPS now. When I first started out as a surveyor, there were 5-man teams to do surveying. Now, 1 man can do it all day long, and he doesn't have to process the data in his hotel room. He plugs it into his computer, and he immediately has a map of his survey. That's how far it has progressed. This is one of the original GPSs. It has Velcro on the back. My brother bought it. He bought it about 20 years ago because he heard there was an airplane for sale, a Fokker 7, in Texas. And the airplane was in perfectly good mechanical system, but its navigation equipment didn't work. So he went out and bought this GPS, stuck a piece of Velcro on the windscreen of the airplane, and stuck this up there and flew that plane from Texas to Fort Lauderdale using GPS. Now, in those days, GPS, uncorrected, when he bought this cheap thing, in those days, GPS was only good to somewhere around 90 to 130 feet. But I'm telling you, if you can't find an airport from 90 feet away, you have a problem. So, actually, the new satellites, the new versions of the satellites, have special channels that are available only to ships and aircraft that improve the accuracy to where that will take them in a dense fog and put their wheels at the threshold line of the runway. How many of you want to get an airplane, try that? No? What is this? Remember I told you, when I started surveying, it was a 5-man crew, and you had to process all that data and do all that math in the field with a stubby pencil. They didn't even have handheld calculators at the time. So you did that in the field using the stubby pencil. I once made the mistake of using a slide rule in the field to do curb and gutter. I ended up being in charge of the instrument from then on, so be careful what you volunteer for. And then some long-haired dude sitting at a drafting table in the evening goes over your math. So you get a math test. Every day you go out and do this work, and you come back and you get a math test at the end of the day. These things, this one says it's good to 1 meter underwater. I haven't tried that yet. But the limitations, just think, you don't have to carry all that gear around. You don't have to slog through the mud when you got one of these. You can always find your car in a Walmart parking lot if you know, mark where you left it. And one of the things, my wife and daughter went out on a mother-daughter trip out to Texas. And as soon as they got out of the car, they turned on the GPS, pressed the button, and says, "Would you like to mark this point?" And they said, "Yes." They were never lost because it tracked them as they moved away from the car, and it left a little green line. If you're Dorothy, you can make it yellow. It left a little green line. All you got to do is get on that green line, and you go right back to your car. It's used in mapping and modeling. Imagine now if you're a geologist and you're tracing a rock outcrop. Believe it or not, if you see enough of that outcrop, you can actually measure the slope of the rock outcrop using this. And guess what? At the end of the day, you come home and you flip this little thing up here and you plug it into your laptop, and you don't even have to do the drafting work. It actually just downloads the coordinates for you. It makes the map, it downloads the map coordinates. By the way, this one you can't do that. You can only use that to fly a Fokker 7. That doesn't work. It's the faster delivery of geographical information systems. I used this cheap thing out on the Missouri River after they rebuilt the levees after the big flood out there. They wanted to mark all of the wells because somebody back in the days, they put the monitoring wells along the Mississippi levees, didn't bother to tell anybody where they put them. So as we're going along rebuilding levees and putting in new monitoring wells, Mikey is going along behind and mapping every single one of them. All I did was, I was out there doing something else. I was a geologist working on the project. But I'd just go out there, turn this thing on and say, take 60 readings, average them together, I'll be back in a minute. And I'd come back, pick it up, turn it off, label that, put the well number on there, and then go on. I casually mapped the monitoring wells along the Missouri River in Iowa, Nebraska, and Missouri. Casually, just while walking along, doing some other job.
What is the well monitored?
What they do is they check the level of water in the wells on the inside of the levees, and they can tell if there's any seepage underneath that way. Oops. And we talked about the centimeter level surveying. Do we have any questions about that? Now, be careful because I'm going to send you a PDF file if you ask me a technical question.
I don't think it's there.
Just all you got to say is send me the PDF.
Now, it's interesting that that example that showed we're sharing with the glass notes,
Uh-huh.
and I assume that's a two-way street.
Yes.
And is there some treaty that got this started? Or is it impossible to, I mean, the thing is up there, we can use it anyway, or?
The last two blocks of satellites don't have secure access code. You'd have to turn the satellite off. Previous to that, the satellites transmitted two signals. One was available to military people, and one was available for anybody who had one. At the end of the war, one of Saddam Hussein's generals said after the Gulf War, "I can't believe you guys came across the desert. All of you came across the desert. Nobody drove up the highway. Nobody came from the sea. You all came across the desert. And plus you all arrived at our lines in battle array. How did you do that?" And so they brought a GPS device into the tent and they showed it to him. And he says, "Your generals have those?" "No, we give them to sergeants." So that was called a secure access code. But now we've decided that you need to have something more than GPS to make an accurate targeting system. And do you think the Air Force can turn those off? They can. They can turn them off. The ones that have the secure access code, they're still up there. There's more than 24 of them up there. So they could turn off the ones. So what the good news is the new satellites are clear access to everybody. The bad news is the Air Force can turn them off.
What about China now?
China has available.
They have a system very much like.
Not that I know of. They might. I wouldn't doubt it. But the GLONASS and the our GPS system are the two most prevalent used in the world. Plus the airline signals that will be available to all airlines all over the world. Even Russian bombers can use it if they want. Yes, sir.
Maybe you have an idea about this. So the GPS on my phone is accurate. You know, they've gotten so accurate they can tell you to change lanes when you're coming to an exit. But I also have on my phone this Find My Friends app that's supposed to let me see where my wife is or to see where I am, and it's not very accurate. Like she'll look and see where I am, and it says I'm out in the woods behind my house or across the street.
That's because it doesn't use the GPS on her phone.
I'm sorry?
It does not use the GPS on her phone. It needs to have 3 cell phone towers within range.
So it goes through the cell tower.
It's the cell towers. It's trilateration from cell towers.
Yeah.
Whereas the one in your car is corrected. The GPS in your car and the GPS in your phone
Yeah.
is corrected. Yes, ma'am.
How come when I'm driving down Sanford Avenue, when I go by those huge satellite dishes, I lose my signal?
I don't know. You lose your cell phone signal, your satellite signal.
Satellite signal.
I don't know. Could be phase interference. I don't know. The new 5G system that they're coming out with. Everybody's heard about this 5G system that's coming out for the cell phones? That is within a tiny, tiny fraction of the kilohertz, megahertz, gigahertz vibration of hydrogen atoms, water molecules. If they ever institute that, your weather reports are going to get horrible if they don't do something about it. Say what? Because the satellites are looking at the vibration of these molecules at a certain frequency. And that's how they map the clouds over the clouds and temperatures over the continents. That's how the satellites do it.
Horrible, why wouldn't it make it better?
Because it'll interfere. The gigahertz frequency of the 5G system is close to the vibration frequency of water molecules. Somebody will figure it out, some bright guy. Okay, can we come back at 10 after 11? Okay, nobody snored, so I assumed I made it funny enough. Here are these GPS systems. Yeah. It was nice for the museum to plan this around my lecture, but they actually have an exhibit in the hallway. And all these exhibits are examples of remotely sensed imagery. And I'm going to tell you that within a certain portion of the spectrum involving ultraviolet all the way to infrared, the multispectral imaging systems can assign red, green, or blue to any band in the frequency. You can get the satellites to choose only certain frequencies to look at. Or you could get all the frequencies and you choose from all the frequencies. which ones you want to look at. Or you dial up the satellite and say, I only want you to look at these 3 frequencies. Why do we map only 3 frequencies at a time? You're going to find that out in this lecture. But anyhow, they have taken multispectral imagery, also called remote sensing. They have taken that and turned it into an art form, coloring the earth however you want to color it, featuring whatever you want to feature. And there's displays of that out there in the hallway, and it's very, very fascinating. And I'll explain to you during the course of this talk how that happens. It's now called remotely sensed imagery. When I first met my wife, she was in charge of the program that taught what was then called multispectral imagery. And it actually awarded college credit. And it went on for a number of weeks, 8 hours a day for weeks. And you got 3 college credits for it. So, I don't know how many times you divide 3 into 240 in order to get the number of hours, college semester hours it would be. But anyhow, it's called multispectral imagery. So the first, we have to understand 2 things. This is the basic lecture that my wife gave to people who were about to receive intelligence products. She briefed these 2 next concepts: spatial resolution and spectral resolution. How big is it? And how can you see it? What does it look like? That's the basic concept that we're going to go through. Anybody have any trouble seeing that? Can you see that in the back? Can you read that? The smallest object which can be resolved in an image. Now, satellites can see things very, very well. When you're doing aerial, by the way, remotely sensed imagery also includes aerial. What it means is it your ability to go out and see something in greater detail than you could possibly see in your own body. How many of you own a telephoto camera? Can zoom out. You are a remote sensing technician when you use that camera to zoom. That's exactly what you're doing. You're in the visible spectrum, but I bet you can buy an accessory for your camera that allows you to do infrared. Can't you? You can. You can buy this infrared device for your camera and point it at your house and see where the heat's going in the wintertime. We're going to have a practical exercise. If you're at the end of your row, and you can do this with him, pull out your driver's license. Take out your driver's license. Just pull out your driver's license. Okay? Just the ones on the ends, I guess. Now, not the person next to you, but the person 1 seat away. I want you to hold your driver's license up and point it at them. Can you read that person's date of birth? Okay. There you have spatial resolution. Okay, that person is probably about 5 feet away. You can put it away now. That person is about 5 feet away. So 5 feet away, you can't see enough to resolve the letters on that person's driver's license. Jane, would you hold your driver's license up and show it to me? If I had the eyes of a hawk, I would tell you that Jane was born in 1981. All you women in this class were born in 1981, right? There's no one here older than 39? Okay. If I was a hawk, had the eyes of a hawk, I could read her driver's license from here. That is, hawks have a better ability at spatial resolution than we do. They can resolve tiny little things at great distances. And why do they have to do that? It keeps them from going hungry. This is our house. It's over on Stillwaters, the cheap part of Stillwaters. I'm retired military. I couldn't afford to live on the lake. This is our house. And what we're going to do, this is from probably, I don't know where the imagery came from, but we're going to talk about that in a moment. But let's take a look at this. This is there's only 3 colors in this picture. Only 3 are being shown to you, red, green, and blue. You're not seeing any other colors. What is that little black thing at the end of the arrow? Anybody have an idea what that is? No, it's the shadow of a transformer on a telephone pole out next to the street. I know that. You don't know that. So how is it possible that you can resolve what that is? You can't. I know how big it is. It's about 3 feet tall. Not yet. God. She had the question, just asked it at the wrong time. What is that? Air conditioner, right. How did you know that? You guessed by its position. That's what a person who does photographic analysis, photoanalyst, would do in the intelligence world. They'd say, okay, that device is stuck onto the side of it. So that must be an air conditioning unit. I know how big that is, but you sure can't tell what it looks like in reality, can you? Not from that picture. What is that? It's a pickup truck. Now, most of you were able to answer that question. So now we know about what size something has to be for you to identify what it is. This little black part here is a shadow inside the bed of the pickup truck. So now we know what's the largest thing we can probably identify in this image. So we would say that the spatial resolution of this satellite image of my house is about 16 to 18 feet. My wife used to tell these generals that that's my husband pushing a lawnmower in the front yard in my dreams. What is that? That's my barbecue grill. I clean it. Actually, I don't think I clean it. But if there was a mouse sitting on top of that barbecue grill, a hawk could see that mouse from over 250 feet away and know that it was a mouse and was waiting to be eaten. What's inside that circle? A mailbox. Where did you get that idea from? You'd be a good photo analyst. See, we're getting to your question. What time of day is it? Now I ask the question. You're looking at the length and the direction of the shadows. The shadows are nearly the height of the trees, and they are pointed at the 11 o'clock direction. So this image was likely taken at 11 o'clock in the morning, right around 11. I know it was taken in March a year ago. Spectral resolution. Now that we know something about what size the things we see, how do we determine what are they? I'm creaking. I look like that guy in the history. How many of you were in the class just before this one? Yeah, you know what I'm talking about, don't you? Yeah. The portion of the electromagnetic spectrum displayed in an image. I'll get down here where I can see these. This is the electromagnetic spectrum. Energy increases with the smaller frequency and amplitude. The smaller frequency. And the increased wavelength. If you rent a condo or lease a condo, or some of you probably own one in Orange Beach or Gulf Shores, you look out over the water and you see the distance between the crests of the waves as they march into the beach, right? That is the wavelength, the distance between crests of the wave. Only a very small portion of the electromagnetic spectrum is available to our eyes. Now, we can sense a little bit more of the electromagnetic spectrum by going to the beach and laying in the sun too long. But that doesn't have to do with eyes. When you look at a map, you're looking at it with your eyes. So all you can see is this tiny little portion of the electromagnetic spectrum. To give you an idea about wavelength, gamma rays have a wavelength roughly the size of a nucleus of an atom. And radio waves roughly have a wavelength the size of whole buildings. Microwaves, like when you go to nuke your chicken at night, have a wavelength probably about your arm span. So when we're talking about wavelength, that's the distance between crests of a wave. Somewhere smaller than the point of a needle and larger than a protozoan is what are the wavelengths of things we can see. That's the visible portion of the spectrum, right in there. Now, you can only see. Computers can only give you something that it sees from a satellite. It can only give it to you if you, as a human being, can see it. If you were a honeybee, you would choose different colors other than red, green, and blue, because you could see something else. But we can't see in the near infrared or the ultraviolet. We just can't see down in those areas. So computers are going to say, okay, if you want to slice up the electromagnetic spectrum anyway, I'll show it to you so that you can see it. I'm going to assign colors of red, green, and blue to whatever you choose to look at in the electromagnetic spectrum. It takes each color that it shows you and it chops it up into different shades. Remember, computers think in terms of 256, is that correct? 0 to 255. There's 256 numbers there, from nothing at all to all of it. But you can't see that. You cannot divide red or gray or pink or any other color. You cannot see more than 16 different shades of that color. After that, you can't distinguish a change. But computers can do this to 256 shades. It can distinguish the change. We know that white light, how many of you now realize that if you go out and you buy a daylight bulb, that it doesn't make your room look so dull? That there's those warm bulbs, I forget what they're called, and daylight bulbs. And the daylight bulbs brighten up your room and make it look real nice and white. That's because the filaments in the daylight bulbs, the LED in the daylight bulbs, are producing more of the electromagnetic spectrum. And you heap all of the electromagnetic spectrum in the visible range, if you heap it all into one place and look at all of them at the highest possible value, you get white. Indeed, sunlight comes in as white because it has the highest possible value of all the colors you can see. If you run that white sunlight through a prism, you get a rainbow. Droplets of water in Virgo, which is falling from clouds, produce rainbows by dividing up the white sunlight into the colors you can see. So let's go back and look at my house here again. Here are all the colors you could see. Now, if the number went down to 0, if the intensity of the colors went to 0, it would be nighttime. New moon, nighttime, cloudy. And if the street light wasn't burning, it would be 0. But if it were on a bright day, like the day this picture was taken, how do we know this picture was taken on a bright day? Shadows, trees, yes. On a bright day, when this picture was taken, if you look at the roof of my house, you will see that it's almost white. How many of you see blue? How many of you see any blue in the top of that house? That's because blue is maxed out, but red and green are just a little bit low. So it's very close to white. Blue makes it all the way to the top, but red and green don't. Red and green together make brown. So that's why you see the forest floor here. Now, the reason our yard is brown doesn't have anything to do with that. So you can take any slice of the electromagnetic spectrum that you can see, any slice of it. You don't have to choose the visible part of the spectrum. You can choose ultraviolet. You can choose infrared. As a matter of fact, we have satellites up there now that break the infrared into 3 layers. Near infrared, which is right in here. Mid-IR, which is right in here. And thermal IR, which is right in here next to your microwave. Remember the thing about wavelength? Thermal is very close to microwave. But a computer, or you can tell a satellite, I don't want to just look at red, green, and blue. I want to look at things out here or over here. I want to look elsewhere. I want to see those things. And when you choose something that I can't see, assign it a color. Give it a color I can see. I can't see infrared. I can't see ultraviolet. The satellite can see it. It can assign 256 different levels to it, but you can't see it. So you just tell the computer, take that slice and give it a color. Blue is worthless when it comes to satellite mapping. Do you know why? The sky is blue. And blue gets diffused in satellite imagery. So what's the first color you want to get rid of? So you say, okay, we're not going to look at blue anymore. That means we have that slot. We can look at something else in place of blue. So we're going to choose near infrared. Why would we choose near infrared? The answer is chlorophyll. If you think the color green looks good to you when the vegetation is healthy, you should see what chlorophyll looks like in near infrared when the vegetation is healthy. So we're going to look at green, and we're going to look at red, and we're going to look at near infrared. How many of you think we're going to assign the color red to red? You're right, we aren't. How many of you think we're going to assign the color green to green? We're not. This is the way we're going to reassign the colors. So we're going to take near infrared and we're going to make it the color red. And we're going to take the color red and we're going to make it green. And we're going to take the color green and make it blue. Makes sense to you, doesn't it? This is the National Capital Area. And it's called false color imagery. That's the selection that I just showed you. And the red color is healthy forest, healthy vegetation. And you're not looking at the color red and you're not looking at the color green. You are looking at near infrared, which glows in the presence of healthy chlorophyll. Lots of chlorophyll, healthy vegetation. So if we had images like this, and we could measure the value of that red, how bright it was, over the wheat fields of Russia, could we not tell you something about the health of their wheat crop that year? Do we do this? We do. Because the economic yes, sir.
Why does the river change color over there?
Hey, listen, guys, if I'm going to have a clack, we need to have a longer meeting so everybody understands. We're looking at vegetation there. And the health of the Russian wheat crop, or the Vietnamese rice crop, or our own corn crop has economic implications. Economic implications have political implications and can therefore help our intelligence community make more informed decisions about what is the standpoint of the person, what is the perspective of the person to whom we are talking to politically. You see the value of multispectral imagery in the intelligence and in the diplomatic community and in the economic community. You can take fields and put different fertilizer on them and take a picture of them at the height of the growing season, and can you tell something about that fertilizer? That's water. Near infrared does not survive contact with water. Water absorbs near infrared 100%. If you see any color in the river or anything like that, it doesn't have anything to do with the water. There's something else there. Now, if you knew how many pixels were in this map, the number of little squares with color in them, if you knew how many there were, and you subtract all of them that are black, then you would know what percentage is land and what percentage is water. Unless there was something in the water. Bill. These are airfields. The reason I point them out is they have big, huge, flat surfaces, just like the roof of my house. So if you knew what the spectral signature was of airfield concrete, then you could take a picture anywhere in the world and you could say, this is what concrete looks like in multispectral imagery. Show me all the areas that have this signature, plus or minus 10%. Subtract everything else out. So what are you left over with? Airfields and superhighways. Then you can say, show me all the areas where there's so many pixels adjacent to one another. Computer will do that, and it'll take out the highways. Dirt in the water. What we have here is upstream of Washington, D.C., in the developed areas in Northern Virginia and in Maryland, where they're building houses and buildings as fast as they can. What is happening to the mud? It's going into the river. And what we're seeing here is a muddy river. So this must be right after a rainstorm or a hurricane or something like that. The military want to know, do our military installations contribute to this problem? Because it's killing off the oysters and the crabs in the Chesapeake Bay. So they heard about me somehow. And they said, will you do a study on the contribution of military installations to the contamination of the Chesapeake Bay? And I was a lieutenant then, so what do you think I said? Yes, sir. Let's take another look at the entire electromagnetic spectrum. And let's say we're just interested in this area here. We have lost a 3,000-pound missile tipped with a nuclear weapon, and we lost it in the desert. So what we do is we go out and we find a similar missile to that one. We lay it on the ground, and we take multispectral imagery photograph of it. And we use everything from ultraviolet all the way up to infrared. And we say, okay, we have a satellite image of that area where we lost that missile. And we know what a missile looks like in near infrared. But we want to be really particular. We don't want to look at street signs made out of aluminum. And we don't want to look at somebody's DeLorean car. We don't want to look at bare pickup truck beds or the metal roofs on people's houses. We don't want to look at that. We only want to look for aluminum painted the same way this missile was. So we slice and dice the electromagnetic spectrum up into 128 different slices. And then we find which three of those 128 different slices produce the greatest signature from the missile that we have in hand. And then we take satellite imagery of the whole area, or aerial imagery where we lost the missile, and we tell a computer, go through this image and point out to me every spot with that spectral image signature. Slicing it up like that into 128 tiny little parts is called hyperspectral imagery. There's three of the 128 slices, and that represents hyperspectral imagery. So if you could divide that square up into 128 little slivers, and then use just those three that you know about to go out and look for something you can't find. Do we do that? We do. When a submarine goes through the water, it leaves a heat signature. I don't care what you power the submarine with, it's going to leave a heat signature. And if you choose just the right spot in the infrared portion of the signature, probably right around thermal infrared, and you take a very thin slice, take one of your own submarines out, run it through the English Channel, take a picture of it, slice it up into 128 pieces, and find the 3 that are most significant to a nuclear submarine passing through the water. Do you see the significance of being able to do this? Low resolution is 60 meters. 60 meters is almost what, 200 feet? So if you're looking at a whole continent, you want to look at, you got your lunch? Did you bring your lunch? You going to the brown bag? Yeah. Anybody needs to go to brown bag, I understand. Not brown bag, what is that called? Huh? Brown bag, yes. Anybody who wants to do that, I'll understand. I'd understand if you left 5 minutes after I started. This isn't the greatest. How many of you are going to think about this tonight when you go to bed? Unless you can't sleep. So if you're taking a picture of a whole continent, you don't want to have billions and gazillion pixels to look at. You'd like just a few pixels to look at. And as long as the piece of land you're looking at generally is about 200 feet by 200 feet, why not choose a low resolution? Landsat does that. Remember all the pictures of the Earth first started coming out? Well, that was the resolution of Landsat. Then there's medium resolution. This is down to tennis court size. Now, when you get down to tennis court size, you're not stuck with 3 colors. Now you got 7 colors you could look at, and some of them aren't colors you can see. And you can take any 3 of those colors and assign them whatever color you want. And if you want an easy demonstration of that, look at the hallway on your way out, because that's what they've done. And there's very high resolution, which gets down to 5 meters. Below 5 meters, you're probably not using a satellite, you're probably using aircraft to generate the imagery. And if you were using aircraft, you could slice it up into 128 slices. You couldn't slice it up into 128 slices from a satellite because it would bleed. The slices would bleed over into the next slice. So when we talk about spatial resolution, now we're talking about the smallest size object you could see on the ground. So there's the visible portion of the spectrum that you can see, the near visible portion of the spectrum that we most exploit when we take satellite imagery, what you see in the hallway. And then there's the extended spectrum. What would happen if you pointed your camera at the sun to take a picture? You'd have a problem. But suppose that you could take pictures of the sun and change it into red, green, and blue. Well, trust me, every time you see a picture of the sun in a magazine or on TV or on a slide or in any presentation in this classroom, it's because it's been changed from extended spectrum into what you can see, which is the visible spectrum. Nanotesla. The Earth's magnetic field. How do you think we detect bombs and stuff that are buried underground? Well, we know what the Earth's magnetic field looks like, and you have a device, and you usually run it north and south, and that device is very happy at home in the Earth's magnetic field until it passes over something that has iron content in it, and then it disturbs the Earth's magnetic field. So you map those disturbances in the Earth's magnetic field, you get the coordinates for them, and then you go out and you put little plastic flags in the ground, and the bullet pickers come later. They tell you to leave, and that's how they look for that stuff. Milligauss, the force of gravity measured by a Lacoste-Romberg gravity meter. The Earth's gravity is not everywhere the same. You want to lose weight? Climb Mount Everest. You will weigh less on the top of Mount Everest. If you want to gain weight, go to the Death Valley. You will weigh more in the Death Valley. Millivolts, strength of an induced field. So you go along and you're mapping along and you're putting the same signal into the ground as you go along. Put the same signal in the ground as you're going along towing this device. That same signal. But all of a sudden that signal touches something, and the thing that it touches conducts electricity. And it sets up its own signal. It decays very quickly, but you induce a signal into the ground, something metal picks it up, it responds to that induced signal, and you measure it. The response comes back in millivolts, thousands of volts. But if you map that, you can go and look for bombs and stuff that aren't made out of iron, that are made out of aluminum, like rockets. Do we have any questions? Do we get to the end of this and everybody's still awake? Can't believe that's true. But okay, I urge you to look at the pictures in the hall. I think you will enjoy how this technique has been morphed into artwork. I cannot believe this happened at the same time we were giving this lecture. Okay, thank you. Sunday, we'll see you next week.